Gravity. We feel it every single second of our lives. But what if I told you it might not be real? At least not in the way we think. Today, we're diving into a mind-bending new idea that reimagines what gravity actually is. So let's just get right to it. What if gravity isn't a fundamental force at all? I mean, this question is at the very core of a new scientific paper, and it's a big one. It challenges everything we've been taught, suggesting that the force holding entire galaxies together might be a side effect of something else. This idea that there are invisible forces holding everything in place, that's not some new, crazy thought. People have been thinking about this for centuries. Take this quote, for example. Today, of course, we've got names for these forces: gravity, electromagnetism, the nuclear forces. But the journey to really, truly understand them, well, that's taken us down some pretty wild rabbit holes.
Okay, so let's get into the meat of it. Is gravity even a force? This new model is basically saying, nope, not a standalone one anyway. The idea is that gravity, well, it emerges from all the other forces we're already familiar with.
All right, let's break this down. The traditional view, the one we all learned, is that gravity is one of the four big fundamental forces of nature. It's a pillar of physics, right? But this new proposal flips that on its head. It says gravity isn't fundamental at all. Instead, it's an emergent effect. Think of it like this. The wetness of water isn't a property of a single H2O molecule. It only emerges when you have a whole bunch of them together. This theory suggests gravity is like that, a large-scale effect that shows up when you have all the other forces doing their thing. And here's the really wild part. This isn't just some idea that came out of nowhere. The clue, the hint that this might be true, has been sitting right in front of us for more than 100 years. And where was it hiding? Yep, in Einstein's own work.
It all comes down to this thing called the stress-energy tensor. Now, don't let the name scare you. We usually simplify Einstein's ideas and say mass tells space-time how to curve. But that's not the whole story. Einstein knew that all kinds of energy and momentum bend space-time. We're talking light, magnetism, nuclear energy, the whole shebang. It all plays a role.
So if you look at the math, Einstein's famous equation is already telling us this. On one side, you've got the curvature of space-time. That's what we feel is gravity. And on the other side, you've got the total energy and momentum from everything. So what this new theory does is take that connection and run with it. It says, hey, what if those other energy sources aren't just adding a little bit to the mix? What if they're the entire reason we have gravity in the first place? And that brings us to a whole new way of looking at gravity. Think of it like a cosmic recipe, where it's not just about one ingredient, but how they all come together. The core idea is actually pretty straightforward. Basically, what we experience as gravity is just the grand, macroscopic result of piling up all the energy from all the other fundamental fields in one place. So what are the ingredients in this recipe? Well, there are four main contributors. You've got the one we all know about, rest mass energy. But then you also have energy from the electromagnetic field, the strong nuclear field, and even the weak nuclear field. They all get thrown into the pot.
Okay, first up, the obvious one. Mass energy. E equals mc squared. It's the energy that's locked up inside every single object with mass. This is the classic source of gravity we've been talking about for centuries.
Next, we have electromagnetic energy. This is the energy you find in electric and magnetic fields. I mean, think about the ridiculously powerful magnetic field around a neutron star, or just the energy in a beam of light. This theory says that energy also helps create gravity.
Then there's the strong nuclear energy. This is the cosmic superglue that holds atomic nuclei together. The amount of energy packed into that tiny space is just mind-boggling. And yeah, that gets added to the gravity recipe too.
And last but not least, we've got weak nuclear energy. This one's a little more subtle. It's involved in things like radioactive decay. But even though it's weak and works over tiny distances, the energy it carries is the final piece of our gravitational puzzle. So if gravity is just the sum of all these different energies, can we actually write a new formula for it, a new recipe? Well, that's exactly what this paper does. And here it is. This is the formula. Now, I know it looks a bit intimidating with all those symbols, but trust me, the idea behind it is super intuitive. Let's pull it apart and see what it's really telling us.
Okay, let's decode this thing. That G on the left, that's just gravity, the final result we're trying to calculate. That big curvy S symbol just means add up everything inside a certain volume of space. And what are we adding up? The rho symbols. Those are just the energy densities, the amount of energy from mass, from electromagnetism, and from the nuclear forces. And those Greek letters, alpha, beta, gamma, you can think of those as the seasoning in our recipe. They just tell us how much each type of energy contributes to the final taste, or, the final gravitational pull.
So you might be thinking, okay, cool equation, but why does it matter? Well, this is way more than just a mathematical exercise. If this idea is right, it could completely change how we look at the universe. We're talking about potentially solving some of the biggest mysteries in all of physics. The biggest change is a total flip in perspective. For centuries, we've seen gravity as a cause. It's a fundamental force that acts on things. But in this new view, gravity is an effect. It's just the macroscopic reaction of space-time to all the energy that's already there. It's not the actor, it's the stage responding to the actors. And the implications of that shift are just huge. For one, it could mean you can have gravity without any mass. All you'd need is a region with a ton of field energy. It could also be the bridge we've been looking for to finally connect Einstein's world of gravity with the weird world of quantum physics, since energy is the one language they both speak. And maybe the most exciting part? It makes a prediction we can actually test. The theory says if you could create a super intense magnetic field, for example, you should be able to measure a tiny bit of extra gravity that shouldn't be there, according to our old ideas. So to wrap it all up, this framework reimagines gravity completely. It's not a primitive, fundamental force anymore. Instead, it's a derivative feature of the universe. It's the consequence of the total energy landscape, a kind of grand cosmic echo of all the other forces doing their thing. And that leaves us with one last kind of mind-blowing question to chew on. If something as real and as fundamental as gravity could turn out to be an emergent property, a side effect of deeper forces, then what else about our reality isn't as fundamental as it seems? What else are we missing?